given some algorithm, how do I describe it in big O notation? How do I find the big O time complexity of that algorithm? The first step is to determine f of n, the number of operations your algorithm performs to solve an input data size of n. So given an input of size n, how many operations does your algorithm perform to solve the problem? Then once you have f of n, if there's any summation of different terms of n, you would drop all lower terms of n. So everything except for the highest term of n, you would just drop it. And then now that you've done that, the last step is to drop constant coefficients. Let's take a look at this simple example. Let's say I have an algorithm where given an input of n students, so input is a list of n students, here's an example, it will first print the length of my list, in other words, print n, then for each of my students, it will print the student's name and print the student's grade. So let's work out what the algorithm does on this simple example. So here I have a list of 3 students, Nima, who has a grade of A+, Ryan, who has a grade of A, and Felix, who has a grade of A. So my algorithm will first print the length of the list. There's 3 students, so it'll print 3. And then for each of my students, so let's start with Nima being student X first, print the name. So it prints Nima, and then print the grade. So I'm just going to print it on the same line, A+. Then now the next student, print the name, print the grade. Now the next student, print the name, and print the grade. So remember, the first step is that we have to figure out what are the number of operations our algorithm is performing as a function of n. So this first step of our algorithm, it doesn't matter if I have 3 students or 10 students or 1,000,000 students. Just printing the length of my list, printing n, is a constant time operation. I'm just printing a single number. So this is exactly one operation. Then for each of my students, well, let's take a look. So for each student, for a single student, I'm printing the name, which is one operation. And I'm printing the grade, which is another operation. So overall, for a single student, I'm doing 2 operations. I'm doing these 2 operations for each of my n students. Therefore, I have 2 times n total operations across all of my students. Therefore, the total number of operations my algorithm performs is f of n equals 2n plus 1. This is the 2n for all of here, and this is the 1 for this first step. Now we have to drop all lower terms of n. So here we have 2 terms of n. We have 2n and 1. So in other words, we have n to the power of 1 and n to the power of 0. We don't see an n here, which means n to the power of 0, which is 1. So n to the 1 is a larger term of n than n to the 0. So we drop this lower term of n. We also drop constant coefficients. So now in my highest term of n, I have 2n. 2 is a constant coefficient, so I drop that as well. What I'm left with is big O of n. Let's take a look at this example. So we have an algorithm where the input is a network of flights across n cities. So here is an example network. We have 3 cities, San Diego, San Francisco, and Seoul. And we have a direct flight between San Diego and San Francisco, a direct flight between San Francisco and Seoul, but no direct flights between San Diego and Seoul. And let's say our algorithm does the following. It first prints a header line that may be sets up a CSV file or something like that, then for each unique pair of cities, it will first print the names of those cities and then print whether or not a direct flight exists. So let's try to work through this example. So first, it'll print the header line. Let's say it's something like maybe like city 1, city 2, direct. Right, so city 1, comma, city 2, comma, direct. And then now for each of my unique pairs of cities, okay, well, let me try one pair of cities, San Diego and San Francisco. So San Diego, I'm printing the names of the cities. San Francisco, and then whether or not a direct flight exists. Yes, a direct flight does exist. Okay, next pair, let's do San Francisco and Seoul. So San Francisco, Seoul, and again, yes. And the last one, San Diego, Seoul, and there is no direct flight, so I would say no. So what is the time complexity of this? This first header line, I can write it without needing to know how many cities there are, and it has absolutely no impact on, or it's not impacted at all by the number of cities. So this is always one operation. Then for each unique pair of cities, okay, let's try just one pair of cities. So for a single pair of cities, let's say San Diego and San Francisco, I printed their names and I printed whether or not a direct flight exists. So let's say I printed 3 items. Let's say that's 3 operations. Even here, we can, maybe let's change this. Let's say this is 3 for 1, 2, 3. Let's say printing the city names and printing whether or not a direct flight exists is 1, 2, 3 operations. And then now I do these 3 operations for each unique pair of cities. So if I have n possible cities, just remembering some mathematical notation, I would have n choose 2, or n minus 1 over 2 possible unique pairs of cities. Basically, n to pick as your first one, n minus 1 to pick as the second one, and you divide by 2 because if I have San Diego, San Francisco, I don't also want to have San Francisco, San Diego. That would be double counting. So n choose 2. And I can rewrite this as n squared over 2 minus n over 2. So I'm doing these 3 operations for each of these n squared over 2 minus n over 2 unique pairs. So let's say this is 3n squared over 2 minus 3n over 2 overall. So first, our function f of n, which is the number of operations versus input size n, is 3n squared over 2 minus 3n over 2 plus 3. So now that I have this, I can drop all lower terms of n. So the lower terms of n here are 3, because this is n to the 0, and minus 3n over 2, this is n to the 1. This is n squared. So n squared is the largest term of n. This one stays. So now that I have 3n squared over 1, I drop all constant coefficients. So in this example, 3/2 is a constant coefficient. So then I get just big O of n squared. Let's take a look at this harder example. Here I have some count variable that I'm initializing, and then while this input variable n is greater than 0, I'm iterating n times, printing out and incrementing my count, and then dividing n by 2. So why is this more difficult? Well, in the previous examples, we were able to basically take what was inside the loop and then simply multiply that by how many times the loop iterated. But the problem here is that the inside loop, this inner loop, actually depends on the value of the outside loop. So it's not that each iteration of the outside loop will have this inner loop going the same number of times. Actually, this inner loop will change how many times it iterates depending on the value of the outside loop. Therefore, we have to do something a little bit more complicated. So let's start with the first line. This one's easy. This, we're only doing one operation. And then now here we have some while loop. This is a little more complicated, so let's just try to figure out what all of this is doing all at once. So this entire nested loop. Okay, so whatever n currently is, I'm doing pretty much n. So let's assume that this here, this printing, let's say this is just one operation, because this is super simple. Whatever n in the while loop is, my for loop will iterate n times, right? So whatever n is, I'll go from 0 to n minus 1. So this loop will iterate n times. And then I'll do this single operation. So basically, the main thing here is if I can figure out how many times this inner loop is iterating overall across every single iteration of the outer loop, that'll be my answer. So whatever n currently is, this inner loop is iterating n times. So the first iteration of this loop, n starts as n, right? So we're going to go based off of this n. We're going to keep saying how many times does this loop based off the initial n. So the first iteration of the while loop, the inner for loop will iterate n times. Then we finish that iteration. The next iteration of the while loop, well, I've halved n, so now half of n is how many times the inner loop will go. Again, n being with respect to this, not with respect to the current value of n. So with respect to the original value of n, because I've divided it by 2, with respect to the original, this inner loop iterates n over 2 times. Now the next iteration of the while loop, my variable has halved again. So with respect to the original value of n, the current value is now a fourth of that. So my inner loop will iterate n over 4 times with respect to the original value of n. The next iteration, n over 8, so on and so forth, all the way until we get down to the beginning. So if we can come up with a closed form equation for this sum, that would give us our f of n function. So it's unclear what this actual value is, and you might think, okay, well, I have nested loops, this is probably n squared or n log n. Don't jump to those conclusions. We actually have to do the math manually. How do we do this? Well, hopefully you remember from calculus, but if you don't, I have a nice trick for this specific example. Let's see what happens if I pull out n from this entire sum. So I'm pulling out an n term from all of these terms. So n times, I divide this by n, so this is 1. So n times 1 is that. If I pull out n here, I get 1/2. If I pull out n from this one, I get 1/4. If I pull out n from here, I get 1/8. Plus yada, yada, yada. And remember, everything we're doing in big O time complexity is assuming n is approaching infinity. It's the limit as n approaches infinity. Okay, so now I have n times this sum. Well, if I could figure out what this sum was, that would be pretty nice. And I have a nice trick for this specific sum where, let's take a look. So 1, let's imagine I'm filling 1 box. So 1 is filling up 1 entire box. Now 1/2, let's say I have a second box and I fill half of it. Let's say now with the 1/4, I have a quarter of the box that I'm filling. Now I'm filling an eighth of the box. Next, a 16th, a 32nd, so on and so forth. This whole sum, how many boxes will be full as I keep going? It approaches 2. So this entire sum in parentheses here approaches 2. Therefore, the total number of operations I perform is 2n. And therefore, in big O, I drop lower terms of n. Well, I don't have any. I drop constant coefficients. This is big O of n. So when you first saw this, you probably thought this was n squared or n log n or something like that because you saw nested loops. And I caution you, you cannot always jump to the conclusion that nested loops imply n squared or n log n. If the inner loop does not depend on the outer loop, you can often make that conclusion, but again, still not always. But in this really weird example, we actually had big O of n, big O time complexity.